Dear students, welcome to the lecture number 10. So today in this talk I shall prove the Tietze extension theorem. So here is the statement. So it says, so let X be a normal topological space and let A be a closed subspace of X, then this theorem actually says any continuous map, so any continuous map, say f from a to -1 to 1 may be extended to a continuous map G from X to -1, 1. That means you have a continuous map, this continuous function from A to closed interval -1 and 1, and this theorem says if X is normal and A is the closed subspace of X, then that function f can be extended to a continuous function G from the whole space X to -1, 1. That is the codomain is the same, but we can extend the domain. Now what do you mean by extended? That's mean G restricted over A is actually the function f. So in other words, that is G, if we take the restriction on A, this is just the function f. Okay. Now to prove this theorem, first of all we need that Urysohn lemma. So what is the statement of the Urysohn lemma? So we can take a different color. So recall that so let X be a normal space, that is normal topological space, and A and B be two closed subsets of X, then the Urysohn lemma says there exists a continuous function say just f from X to, you can say 0, 1, such that f of A is just that one in point, that is singleton 0, and f of B is the other in point, that is singleton 1. Now tell me, is there any specialization for that closed interval 0, 1? So there is no specialization on the set, that is right 0, 1. Now since that 0, 1 is actually, that space is homeomorphic to any closed interval AB, right? So we can replace that 0, 1 by the closed interval AB. That's mean we can say there exists a continuous function, say some G, say x to any AB such that f of A is that singleton A and f of B is singleton B. Right? So we can choose any AB. So we can choose any A less than B in R. Right? Oh, sorry. Here it should be G, right? Fine. Now this is just the Urysohn lemma. Now we shall use this lemma. Okay. Now first of all, so to prove this theorem, that is that Tietze extension theorem. So what is this theorem? This theorem says if you have a continuous function f from a to closed interval -1 to 1, then it can be extended to a continuous map G x to -1, 1, right? Now we shall prove this theorem by using several steps. Now in the first step, we shall first consider one continuous function, a different continuous function, say capital F from A to -r, r. So this is my step 1. So we shall use this step again and again, okay? So step 1. So let say some capital F A to -r, r be a continuous function. Okay, and what is my A and X? So this A and X is given. So here X is a normal space and A is a closed subset of X. So why such a map exists? So we just assume that if you have a function capital F from A to -r, r, then you get a G. Okay. Now let you have a function f from A to -r, r, then we claim that so there exists another continuous function right. So if you have a continuous function from A to -r, r, then you have a continuous function G. We can write it is a capital G from the whole space X2, and my codomain will be -r/3, r/3. Okay. Continuous function this such that G of A minus f of A, that is their difference, the difference between G of A and my that f of A, their modulus value is less than equal to 2/3 into R, and it is true for all A belongs to what, X? No, because f is not defined on X, right? F is defined on A, right? So we said their difference is less than equal to 2/3 into R for all A belongs to A, right? Okay, now we will prove this one. Now how to prove this? So first of all, see, we have a codomain, right? My codomain is minus r comma r. So this is my minus r comma r, right? Now what we are planning? We are planning to restrict the codomain, right? Not restrict, but we are planning to find another function g whose codomain is minus r by 3 comma r by 3, right? So you can see that the length of this codomain is just the 1/3 of the length of that, right? So that is the reason. So we shall first divide this interval, that is minus r comma r, into 3 equal parts. So it is minus r to, say it is minus r by 3, say it does not look like 3, right? So this, okay, say this is my minus r by 3, say this is r by 3, and this is r, right? Now say this is my I1, say this is my I2, and say this is my I3. Okay, now write mathematically. So we first divide the interval minus r comma r into 3 equal parts. So say I1 equal to, say, minus r comma minus r by 3. Okay, say I2 equal to minus r by 3 comma r by 3, and I3 equal to r by 3 comma r. Okay, fine. Now just look at G. Here my codomain is from x to minus r by 3 comma r by 3, right? That's mean we shall define G from x to the I2, right? X to the interval I2. So that's mean we need I2, but we don't need I1 and I3, right? Now we do something with that I1 and I3. So what I shall do, so now let B equal to my F inverse I1 and C equal to F inverse I3. Now what can you say about B and C? Look at, so what is my F? So F is a function, I can take a different color, okay. So F is a function from A to minus r comma r, right? And we divide this r comma r into 3 portions, 1, 2, 3, right? Now we have taken this portion and take the inverse image. We have taken this portion and the inverse image. So inverse image of this portion is B and inverse image of this portion is C, right? So that's mean B and C are closed set in A, right? Obviously they are closed sets in A, right? Okay. Now they are closed sets in A. So what does it mean? But we know that A is also closed. That's mean B and C are also closed in X. Fine. Now since I1, I3 are closed in the domain, say minus r comma r, and if is continuous, that imply B and C are closed sets in A, right? Now also it is given that A is closed in X. Since A is closed in X, That imply B and C are also closed in X. Fine. Now also, can you see that B and C are disjoint? This is also simple, right? Because B, the image of B is I1 and image of C is I3. They are disjoint, right? Also, V and C are disjoint. Right? Okay. Now B and C are closed sets in X and they are disjoint. So what we can do? Now we can just use, that is, we can just find an Urysohn lemma, right? We can use that in Urysohn lemma. Now if we use the Urysohn lemma, look at that Urysohn lemma. So this is my Urysohn lemma. So what A and B we shall choose for my G? Obviously, my required codomain is minus R by 3 and R by 3, right? So that's mean my A should be minus R by 3 and my B, that is small b, should be R by 3. That is the simple, right? Sorry. So therefore, thus by Urysohn lemma, there exists a continuous function G from X to, we can choose any AB, right? So we will choose the AB is minus R by 3 comma R by 3. Why? Because we need that, such that G of V is minus R by 3, that's singleton, and G of C is R by 3. Right? So we got that required G. Right? Now, just only point is to check that. Which point? So we need to just check that GA minus FA less than equal to 2 by 3R. So we need to just check that. Right? So this property is done. We need to check only this. Fine. Now claim that so f of A minus G of A is less than equal to 2 by 3 into R for all A belongs to A. Now why that is true? Okay. Now this is actually a simple one. Why? Because so if A belongs to A, that's mean we have three possibilities, right? So for any A belongs to A, we have three possibilities. Oops. Three possibilities. So either A belongs to B, or A belongs to C, or A belongs to A minus B union C. Right? Now what if A belongs to B? Now if A belongs to B, then f of a, so what is my f of a? So f of a belongs to, so what is my b? B is f inverse, see, look at what is my b? B is f inverse I1, right? So if a belongs to b, then f of a belongs to I1, right? So this belongs to minus r comma minus r by 3, and g of a is equal to minus r by 3, right? So that implies mod of f of a minus g of a is less than equal to 2 by 3 into r, right? Clear? This is, if no, then also we can do this one. So okay, I can do precisely. So it is here minus r less than f of a less than equal to minus r by 3, right? Now since g equal to minus r by 3, that implies minus r plus r by 3 less than equal to f of a minus g of a, now less than equal to, so minus r by 3 plus r by 3. Now that implies minus 2r by 3 less than equal to f of a minus g of a less than equal to 0, right? So their modulus is less than equal to 2 by 3 into r. Fine. Now similarly, if a belongs to c, then f of a belongs to r by 3 comma r, right? That is I3, and g of a equal to r by 3. So what is the difference, f a minus g a? Now similarly, we can prove that mod of f of a minus g of a is less than equal to 2 by 3 into r. Now what if my a belongs to that a minus b union c? So that implies f of a belongs to I2 belongs to, that is equal to minus r by 3 comma r by 3, right? And this is the same as g as well, right? So that implies, so f of a comma g of a belongs to that interval minus r by 3 comma r by 3, right? So their difference will be the diameter of this set, that is the length of this set. So that implies mod of f of a minus g of a less than equal to 2 by 3 into r. So we are done. So step 1 is done. Now during the proof we shall use this step again and again. That means we shall change that r and we will get a g. Just remember that for each r and for a f we are getting a g with this property, right? Now during this proof we shall use this r, that is we shall change my r and we shall change my f and we will get a new g. Okay, fine. Now here is my step 2. Okay, now what is my given condition first of all? So now again go to the main statement of this theorem. See what is my statement? My statement is, it is given that f is a small f is a continuous function from a to minus 1 comma 1, right? That's mean we can use my step 1, right? What is my step 1? In step 1 we have a function capital A from A to minus r comma r, right? So if I want to use step 1, so what r we need to choose? Obviously r equal to 1, right? Now given step 2 is given if A to minus 1 comma 1 a continuous function, right? Now by using step 1, so taking r equal to 1 and by using that step 1 we get a g, right? But here we can rename that g because it depends, it is a particular, right? So we get a continuous function say it is my g1 from x to where? X to, see what is my the codomain of capital G? So my codomain of capital G was, see, minus r by 3 comma r by 3, right? So we get a G1 from x to minus 1 by 3 comma 1 by 3. Minus 1 by 3 comma 1 by 3 and mod of f of a minus g1 of a, that is less than equal to 2 by 3 into r, where r my 1, right? R is 1, so it is just 2 by 3 for all a belongs to a. Fine. Okay. Now here you can just say that mod of g1x is less than equal to also what? 2 by, no, it is, what will be the modulus of gx? It is from minus 1 by 3 to plus 1 by 3, right? So their modulus value is 1 by 3. Fine, for all x belongs to x. Anyway, so we have a function f minus g1, right? That is less than equal to 2 by 3. Now we shall repeat the argument again and again. Okay. So now we have a continuous function f minus g1, that is my continuous function from a to minus 2 by 3 comma 2 by 3. Here my r equal to 2 by 3, right? So therefore by taking r equal to 2 by 3 and using step 1, we get a continuous function g2 from x to where? So x2 we know it is minus r by 3 comma plus r by 3, right? So here my r is 2 by 3. So it will be minus 1 by 3 into 2 by 3 comma 1 by 3 into 2 by 3, right? And mod of fa minus ga g1a, so that was my previous function, and minus g2 of a, Now that is less than equal to 2 by 3 into r. So 2 by 3 into r. So what is my r? R is 2 by 3. So that is 2 by 3 whole square. Right? Now here g2x is less than equal to 1 by 3 into 2 by 3 for all x belongs to x. Okay. Now, so similarly we can find g3, g4, g5, right? But this is not a mathematical way to proceed. Now we shall use the mathematical induction for the existence of gn for all n. Okay. So first of all, let Sn be a statement. So let Sn be a statement that gn, a function, exists. So gn, so we can write a statement, a continuous function gn exists such that so we have these two properties. So gnx is less than equal to 1 by 3rd into 2 by 3 into n minus 1 for all x belongs to x, and mod of f of a minus g1a minus up to gna is less than equal to 2 by 3 whole to the power n for all a belongs to a. Okay. Now just recall that by our construction Sn is true for n equal to 1 and 2. Right? Now we have seen that Sn is true for n equal to 1 and 2. Right? Now assume that Sn is true for n equal to k. That is gkx less than equal to 1 by 3 into 2 by 3 power k minus 1 for all x belongs to x, and f of a minus g1a minus up to gka, that is less than equal to 2 by 3 power k for all a belongs to a. Right? Now we claim that Sn is true for n equal to k plus 1 as well. So therefore, so this is a function. So that my f minus g1 up to gk is a function from a to, so minus 2 by 3, this is power k, comma 2 by 3 power k. So this is a continuous function. Right? So therefore by step 1, so by taking r equal to 2 by 3 power k and by using step 1, we get a continuous function g2 gk plus 1 get a continuous function gk plus 1, right, from x to where my 1 by 3 into r, right? So 2 by 3 power k, comma 1 by 3 into 2 by 3 power k. This is my continuous function, and that is f of a minus g1a, so minus gka minus gk plus 1a, that is less than equal to 2 by 3 into r. So 2 by 3 into r, so this is my r, so that is 2 by 3 into k plus 1, right? So for all a belongs to a, and here, so gk plus 1 x, that modulus is less than equal to 1 by 3rd into 2 by 3 power k for all x belongs to x, right? So therefore the statement Sn is true for n equal to k plus 1. Thus, by the principle of mathematical induction, we can say, so Sn is true for all n belongs to natural number. That's mean g1, g2, g3 all exist. So that implies g1, g2, g3 all exist. Okay. Now we define, see, we need to define a extension, right? Now we define a function g from x to, so we don't know which is the domain, so we just write here just r. So we have to see what is my codomain. Okay, so here we can write just r such a way that g of x equal to summation of n equal to 1 to infinity gnx. Okay, now just check what is the domain of g. That imply mod of gx is less than equal to summation of n equal to 1 to infinity mod of gnx, right? Now what is my gnx? So we know that, you can see, gnx is less than equal to 1 by 3 into 2 by 3 power n minus 1. So that implies it is less than equal to, so it is 1 by 3 summation n equal to 1 by 1 to infinity, so 2 by 3 n minus 1, right? So it is just 1 by 3 into 1 plus 2 by 3 plus 2 by 3 square, this geometric series, right? So what is the sum of the geometric series? It is 1 by n into, it is 1 by 1 minus r, right? Here r is 2 by 3. So this is just 1. So that implies mod of g of x is less than equal to 1 for all x belongs to x, right? So we can say g, right, is a function from x to where? Minus 1, 1. Now this part is done. Fine. Now we need to show that g is continuous. So first of all we need to show that g is continuous. Okay, so how to prove that G is continuous? Now again let so say Tn equal to G1 plus G2 plus up to Gn be the partial sum of the series of function summation n equal to 1 to infinity Gn x, right? Now obviously each of Tn is continuous, right? Now since each Gn is continuous, therefore Tn is continuous. Right? Now for any k bigger than n we have, so what is my tkx minus tnx. Okay, so this is just mod of summation over say I equal to n plus 1 to k g of ix, right? But we know each of gix is less than equal to 1 by 3 into 2 by 3 power I minus 1. Now that is less than equal to, we can just write 1 by 3 summation I equal to n plus 1 to k, it is 2 by 3 power I minus 1. Now if we take that 2 to the power I minus 1 outside, that is the first term is 2 to the power 2 by 3 power n, right? Now if we take that outside, then we will get, it is 1 by 3 into 2 by 3 power n, and then that summation will be, or you can just write, then that this term will be 1 plus 2 by 3 plus 2 by 3 whole square in this way, right? So up to 2 by 3 power k minus 1 n minus k plus 1, right? So sorry, k minus n minus 1 or something like that. I have to check that term. Anyway, so that is less than, you can write 1 by 3 into 2 by 3 power n, and we take that infinite series. So 1 plus 2 by 3 plus 2 by 3 square plus dot dot dot, this one, right? Now what is that sum? So equal to 1 by 3 into 2 by 3 power n, and this sum again 1 minus 2 by 3. So this is equal to 2 by 3 power n. So that imply actually we get mod of tkx minus tnx less than 2 by 3 power n, right? So for all x belongs to x, where that k is bigger than n, right? Now since that right term does not depend on k, right? It does not depend on k. So taking k tending to infinity, we have that is g of x minus tn of x is less than 2 by 3 power n for all x belongs to x. Right? Now here, obviously, now for any epsilon, obviously then for any given epsilon bigger than 0, there exists capital N such that mod of gx minus tnx less than epsilon, or we can write it is here, for all n bigger or equal to that natural number n. And also this is true for all x, and further same n will work for all x in x, right? So that implies that Tn, that sequence of function, converges to G uniformly. So uniformly. Since Tn converges to G uniformly and each of Tn is continuous, so G is continuous. Now since each of Tn is continuous, so G is continuous, right? So therefore we get a continuous function. So therefore we get a continuous function g from x to minus 1 comma 1, right? Now we just need to check that GA equal to FA. Now we need to check that G of A equal to F of A for all A belongs to A. Now this is also true. Why? Also by our construction. So by our construction, so for any A belongs to A, we have F of A minus G1A minus G2A minus GNA is less than equal to 2 by 3 into n, right? So that implies mod of F of A minus, this is my Tn of A, less than equal to 2 by 3 n. So that implies Tna converges to F of A, right, for each A. Now since Tna, that is converges to G of A, or we know this is true for all x, right? So Tn of x converges to G of x for all x belongs to x. So we have G of A equal to F of A for all A belongs to A. We can write here for each A belongs to A. Right, so we get a continuous function g from x to minus 1 comma 1 such that GA equal to FA for all A in A. So that implies G is a continuous extension of F. fine. Now, so this completes the proof. Okay. Now there is one note for this one, for this theorem. So is there any speciality of the closed interval minus 1 comma 1? Exactly no. Because, so here I can note, I can take a note that now since that open closed interval minus comma 1 is homeomorphic to any closed interval AB for any A less than B in R, right? So therefore we can generalize that statement a little bit. We can say for any normal space X and for any closed set A in X, any continuous function f from A to just take closed interval AB in R may be extended to a continuous function G from X to AB. So what is the proof of this one? So if there is a statement like this way only, so we first take a homeomorphism from AB to minus 1 comma 1, right? Now take the function, that is the revised function from A to minus 1 comma 1, and we proved that Tietze extension theorem as previously, and then again we push back the main function by composing the reverse of the homeomorphism, right? Okay. Now there is another version of the Tietze extension theorem. It says, so it is another version actually. Now it says any continuous map. So first of all again, so let X be a normal topological space and A be a closed set in X, then any continuous function f from A to R. So here I am not writing closed interval minus 1 comma 1. So here I am writing R, right? So any continuous function from A to R again may be extended to a continuous function G from X to R. So that's mean even if you choose the codomain as R, that is not only that closed interval AB and not the minus 1 comma 1. So if you assume the codomain is R, then also you can get a continuous extension from G X to R. So the proof is little bit tricky. Tricky means just one trick. So we have to apply the previous version and there is a trick. So what is that trick? So here is the proof. Okay, so first of all, so given all of this, right, so we know that R is homeomorphic to -1, 1 open interval, right? So now let H from R to -1, 1 be a homeomorphism. Okay, now then if we take the function composition that f with h with f, if we take this function, then this will be a function from a to where? -1, 1, right? Now we can consider this function f. So we can consider function f to -1, 1, again subset of -1, 1 closed interval, right? So then f is a continuous function from a to -1, 1, right? So by the previous version, we get a continuous function say g from x to -1, 1 such that g of a equal to f of a for all a belongs to a, right? Now what is my capital F of a? We know that f of a subset of -1, 1. Now since f of a is subset of -1, 1, that implies g of a is actually subset of -1, 1, right? For all a belongs to a. Fine. Now let D be the function g inverse -1 union g inverse singleton set 1. Okay. Since that 1 and -1 are closed set in the set -1, 1 and g is a continuous function, therefore D is closed. D is closed where? In X. Now also given that, A is closed in X, right? So A is a closed set in X and D is a closed set in X. Now from this, we can also say that A intersection D is empty. Why? Now since image of A is just subset of -1, 1 and image of D under the continuous function G is just, we can say it is subset of set 1, -1. Therefore we can say A intersection D should be empty. Now therefore A and D So therefore A and D are two disjoint closed sets in X, right? So we can use the Urysohn lemma. Now by Urysohn lemma, so there exists a continuous function say phi from x to 0, 1 such that say phi of A is singleton 1 and phi of D is singleton 0, right? Now again we define a continuous function psi x is just phi x into g of x. So why psi is continuous? Because phi is continuous, g is continuous, and psi is the product of these two functions. Now you can just note that. So since phi and g are continuous on x, so psi is continuous on x. Now we claim that function psi is a continuous extension of the function f. That is, we claim that psi of A equal to f of A for all A belongs to A. So why this is true? Because for each A belongs to A, what is my psi A? So psi A equal to, just by definition, it is phi A and g of A. Now what is phi A? So we know phi gives the value only 1, right, on the set A. Therefore it is 1, and we know GA equal to FA because G is a continuous extension of F. So it is just f of A. So f of A. Right? Now what is the codomain of psi? Now we claim image of psi is subset of -1, 1. First of all, note that so phi is a function from x to 0, 1, right? So that implies, let's say mod of phi x less than equal to 1 for all x belongs to x, right? Now we claim that mod of psi x is strictly less than 1. Why? Because, so now choose a point x in capital X. That is the whole set. Now we have two possibilities, right? Either x belongs to D or x belongs to D complement. Now if the first case arises, that is if x belongs to D, that implies what is my phi x? Now phi x just 0, right? By the construction. Now what will be my psi x? So psi x will be my phi x into gx just 0, right? Now what if my x belongs to D complement? Now if x belongs to D complement, that implies we have already that phi of x is less than equal to 1 and mod of gx is strictly less than 1. Why mod of gx is strictly less than 1? Because as my D is the set of G inverse 1, -1. That's mean, see what is the image of D? Image of the set, image of the continuous function G, that is the set -1, 1. right? That closed interval minus 1 comma 1. But what is my d? D is just g inverse 1 comma minus 1. That's mean if x is not in d, then image of x cannot be 1 or minus 1. So what is the only possibility? So only possibility is gx is lies between 1, minus 1 and 1. That is open interval minus 1 comma 1. Right? Now then mod of psi x, which is just mod of phi x into mod of gx. Now that is less than equal to mod of gx, strictly less than 1. Right? Now that implies psi is a function from x to minus 1 comma 1 is a continuous function such that psi of a equal to my f of a for all a belongs to a. That's mean psi is a continuous extension of the function capital F. Right? Now what is my f? F is a function from x to minus 1 comma 1. That was my f. Right? Sorry. That was my f. Right? And here I had that H inverse from this to R. Right? So we have chosen my H is a homeomorphism from R to minus 1 comma 1. So here it is H inverse. And also what is my psi? So here x to minus 1 comma 1. So that is my psi and that is my H inverse. Right? Now since psi is a continuous extension of f, that implies continuous extension of f, therefore H inverse psi is an continuous extension of H inverse f. Now what is my H inverse f? So we know H inverse, we know my f is H compose f, right? So that is just f. Now let g equal to that function, that is H inverse compose psi, which is a function from x to R. So therefore then g x to R is a continuous extension of the function f a to R. Okay, so this completes the proof. So we are done. So I stop here.